So if anybody misses this, we will have it. We're going to talk about equilibrium. And you are going to tell the person next to you or someone near you, what is an equilibrium? What do you know about equilibrium? Okay, what kind of reaction do we have if we have an equilibrium? Opposing force, what kind of reaction do we call that? We call it starts with an R. You guys didn't watch the video. Reversible. How could you have an equilibrium without a reversible reaction? So when we have a reversible reaction, what kind of an arrow do we use? A two-way arrow, and it looks like this. We sometimes call it a double harpoon, okay? You will sometimes see it look like this because it's hard to find a font that has this particular character in it. Or you may even sometimes see it look like this. Those are not as correct. This is the best choice if you're writing it, okay? If you're typing it, you go with whatever you can find that works, okay? What is equal in an equilibrium? The forward rate and the reverse rate. So the forward rate, let me make sure I'm recording. I am, yay, is equal to the reverse rate. Is the concentration of products equal to the concentration of reactants in an equilibrium? No. Okay, and in fact, you will see a situation today, where that is not the case, okay? And in fact, equilibria can sit at many different positions where sometimes you'll have an equilibrium where you have lots of reactants and very little product. And other times you'll have a relatively even distribution, and other times you'll have lots of products and very little reactants. So what is true is that the forward rate is equal to the reverse rate. So if we had an equilibrium, A in equilibrium with B, the rate at which A is consumed The rate at which A is consumed, how does that compare to the rate at which A is produced? So you get to choose is greater than, is less than, or is the same as. Is the same why? Because it's at equilibrium and the two rates are the same, right? The two rates are the same, so it will be is the same as. I should say here at equilibrium. EQM is equilibrium, okay? So what can you say about the concentration of A as time goes on? It stays the same because we're producing it at the same rate as we are using it up. Yes, it stays the same. Could we make the same argument in regards to B? Yes? We're good with that? Okay. These guys over here are just answering all my questions. Do you guys over here feel good with that? Okay, same argument for B. For B. Okay. So although the concentration of A and the concentration of B aren't equal, they remain constant. Yes? At equilibrium. Concentration of reactants does not equal concentration of products, but the concentrations remain constant. All right, and we are now going to take a look at a system that contains, here is our demo, and we are looking at some tubes and they contain a brown gas, which you will see in just a moment. Let's see, here we go. Brown gas in the tubes is NO2. Okay? Brown gas in the tubes is NO2. And for those of you watching the video, this is going to get pretty boring at this point. There will be videos on this. You can look up the equilibrium later. But anyway, I'm going to turn on the lights so you can see them better. So here are two tubes containing the NO2 brown gas. What can you say about the color of these two tubes? They are brown. What can you say about the intensity of the color in the two tubes? Not very high capacity. Compared to one another, what can you say? They look approximately the same, yes? Okay, so we have the same color. Now, hopefully, I have here some ice water. And yes, my kettle has boiled. That's excellent. I'm going to pour us some hot water here. And if you're at the back and you cannot see, please feel free to come forward to the front. There's lots of room here. There's lots of room here. Okay, don't be shy. You'll get a much better view. Okay. Just don't stand in front of anybody. But if you stand behind me, you won't be in front of anybody, okay? Now, so this one is hot, this one is cold. This is confusing me because in my other blocks it was the other way around. I had the beakers switched around. Can I do that so I don't get confused? Okay. Hot, cold. What are you guys noticing about the two tubes now? Right? And I'm actually going to reverse them so that the whole tube is now getting the temperature difference. Okay. Alrighty. Now what does the intensity of the color, so this one's lighter, so this is less intense color, this one's darker, it's more intense color. What does that tell you about the concentration of the brown gas? Which of these has a higher concentration of the brown gas? The one that's in the hot water, yes? Higher color intensity, that must mean there is more brown gas in there to make it darker colored, yes? Now, what kind of a system is this? Is it open or closed? It's a closed system. So my question to you is then, where is that extra brown gas coming from? And over here, this is lighter than it was before, yes? Where did the brown gas go? How is that possible? Don't forget, we're dealing with reversible reactions. Uh-huh. But a reaction always needs something and something. It needs reactants and products. And so far, all I have told you about is a brown gas, yes? However, there is also a colorless gas. Okay? In the tubes. Now, do we want to switch them up and see what happens? What do you think is going to happen? Ooh, look at that. You kind of get like a half and half effect. Yeah. And in fact, if you were to come up close, you could actually see in the hot one, you can actually see the brown gas kind of rising from the hot area up into the other area. Okay, so what's happening is that we have both the brown gas and the colorless gas, and the position of the equilibrium is changing depending on which temperature we have. All right, you guys can go sit down again, and we're going to write a little bit more. And the colorless gas in the tubes is N2O4. So what we have is we have an equilibrium we have N2O4 in equilibrium with, whoa, sorry about that, 2, okay, it's not liking my glove. There we go, that's better. N2O4, no, not N2O4, NO2. However, in order to balance that, what do we need to do? Put a 2 right here. What is wrong with my pen? Oh my God. 2, there we go. Okay, good. So what this would look like is it would look like We would have an N with an O and another O. This is really behaving badly. I'm sorry. And here we have another O, N with another O and another O. And at some point, those two will collide and a bond will form. All right? And when that bond forms, instead of having two separate NO2 molecules, we're going to have an N and an O and an O. And that'll be bonded to another N and an O and an O. And now we have an N2O4. Yes? At room temperature, what can we say about the color? The color was changing or constant? It was constant. Therefore, what can we say about the concentration of NO2? Not changing, constant, okay? Therefore, what can you say about the rate of the forward and the reverse reactions? They were the same. So we were at an equilibrium. Now, for today, because we don't have a lot of time, we're just going to talk about the transition to hotter temperature, okay? When we increase the temperature, what happened to the color? Color got darker. Therefore, what could you say about the concentration of the NO2? That's the brown stuff, remember? Got higher, yeah. So what does that mean about the forward and reverse rates? And I'm going to rewrite the equation here. I'm not going to draw in the colors because I just don't have time in my life for that anymore. Too many buttons to push. Therefore, the forward reaction, forward rate, how does it compare? Is that a greater than, is it a less than, or is it an equals to? If NO2 is increasing, so we start with some NO2, and then we end up with more NO2, and then we end up with more NO2. Which rate was faster? The forward rate, because we are producing NO2. If NO2 is getting higher, we must be producing it faster than we are using it. Now we're going to go back to reaction rates for a moment, and we'll do like a little review. One of the things that you might need to know for next week's test. And that is what happens to rate reaction rate when we increase temperature, and why. Tell your partner. First of all, what happens to rate? It increases. Why? There's more kinetic energy, so the particles are moving faster. And if that's the case, what happens? There's more collisions. Higher frequency of collisions. And also, not only are there more collisions, but what else? Tell your partner, what else? There is a higher what? Higher percentage of collisions which will be successful. With sufficient energy to be successful. Sufficient energy to be successful. Okay. So, remember what we just said a moment ago. We just said that when we increased the temperature, the color got darker, and that meant that the forward rate had to be bigger than the reverse rate. So, in regards to this equilibrium system, N2O4, in equilibrium with 2 NO2, whoops, I should say when we increase temperature, what happened to the A forward rate? It increased. Yes. Are we all good with that? Forward rate increased. When we increase the temperature, what happened to the reverse rate? So when I increased temperature, rate decreased. That's not right, is it? No. So the reverse rate, it has to also increase because you're still going to have more collisions, you're going to have more energetic collisions, and so the rate is still going to be faster. So the reverse rate also increases. What is wrong with this pen? It's driving me crazy. Increases. There we go. There we are. That's better. So how is it that both rates increase, but we're making product faster than we are using it? How is that possible? Yeah, the forward rate increases more. They both increase, but the forward rate increases more. So if this was our original reaction, N2O4 to NO2, what I'm going to do is I'm going to make the arrow bigger to show an increase in rate. Okay? So when we increase the temperature, my forward rate increased, yes? My reverse rate also increased, just not by as much. And what that means is that both rates are faster than before, but the forward rate is faster than the reverse rate is. And we're going to draw a graph of that now. We're going to draw what we call a rate diagram. So we got rate, and we got the progress of the reaction. Now, initially, when we were at room temperature, were we at equilibrium at room temperature? Yes, the concentrations were remaining constant, and we were at equilibrium. If that is true, what can you say about the forward rate, which I'm going to do as a black line, and the reversed rate, which I'm going to do as a dashed red line? At room temperature, what was true about those two rates? When we were just at room temperature, before we started doing anything, and they were just sitting there. They were equal, yes? Because we were at equilibrium. So the rates were steady and equal. And constant. And I'm actually going to make that go on a little longer because I need more room to write. There we go. Now, all of a sudden, at time t, okay, we increased the temperature. What happened to our forward rate when we increased the temperature? It increased. What happened to our reverse rate? It also increased. The same amount? No, not as much. So at this point in time, what can you say about NO2? At time t, will the concentration of NO2 increase, decrease, or stay the same? Concentration of NO2 will increase, yes, because we're making it faster than we are using it. Now, if the concentration of NO2 is now increasing, what happens to the forward rate? Or not the forward rate, the reverse rate. Let's say the reverse rate. Oops, I forgot my two. There we go. 1, 2, and 2. So if I have more of this, right, as time is going on, my NO2 is increasing. I've got more of it. What can you say about the rate of this reaction in that direction? What can you say about the number of collisions? If I have more NO2, more collisions. Therefore, what happens to the rate? It increases. So, originally the rates change because we changed the temperature, yes? And in response to that, the concentrations change, yes? Because now one rate's faster than the other. And now because the concentration is changing, the rates are going to change again, yes? So what we're going to see then is that we're going to see that you see these sharp changes in the rate? That's because we changed the temperature. And now, as we make more of the product, so as we have more product, the reverse rate is going to increase. And as we use up N2O4 faster than we make N2O4, yes? As I'm using up my N2O4, what's happening to the concentration of N2O4? It's decreasing. And if it's decreasing, what's happening to the rate of the forward reaction? Hold on, if N2O4 is getting smaller, the forward rate is going to decrease. I have less N2O4, therefore there's fewer collisions. And eventually, what happened? What's happening to the concentration of the brown gas and the colorless gas now? Is it changing? No, it's now at a new equilibrium, right? And we can see that because, why did I draw that one as a dashed line? Dash it all. We now have a new equilibrium. Is established. And the position is more towards the products. The position of the equilibrium is more towards the products. The position of the original equilibrium was more towards the reactants. And if we cool it, it becomes even more so towards the reactants. Yeah, and we're going to start talking next week about the stress and the response. So we stressed the system by changing the temperature, and then the system responded by shifting and making more of the product and less of the reactant until the rates balance out again. Okay? You guys got the most coherent of these lectures of all of them. So give yourself a pat on the back. There will be some stuff for you to do for homework in terms of Unit 2. It's not long, okay? But it will be posted online because I didn't manage to get it printed today because I had issues with printing, okay? Huh? Yes. Yeah. Okay, I will, yeah, number. Come on, I need to stop recording. Stop recording.